Welcome back. And in the next part, we're just going to look at some more examples. This time, we're going to look at a couple of rational functions. These, again, are going to be a little bit worse than the polynomial from the last video, but relatively nice because these are things where we have a lot of pre-calculus knowledge to come to bear on this. So, for example, I know with rational functions, I'm expecting likely that there's going to be some asymptotes, and I have an idea generally of what I can expect to see. Let's do the pre-calc side of things first. So firstly, I know that there's going to be, as far as intercepts go, x-intercepts happening when the function is equal to 0. And a rational function is only equal to 0 when the numerator is equal to 0. And the top is then only ever equal to 0 when x cubed is 0, which happens to be when x is 0. This would also turn out to be, of course, the point y equals 0, x equals 0. In other words, it's both the x-intercept and the y-intercept. So our graph is crossing the axis, both axes in exactly one place, just at the origin. If we're thinking about vertical asymptotes, I know that I would have one if the denominator were ever equal to 0, and it certainly can be, and only in one place though. Only at cube root of -1, which is -1. So I'm going to have a vertical asymptote, and it will be the line x equals -1. Okay, so we've done all of our sort of pre-calc side of things. Let's start doing the calculus side of things and think about horizontal asymptotes. And for this one, I mean, you could answer this using pre-calculus, because in pre-calculus we would have said since the degrees of the top and the bottom are the same, then yes, we'll have a horizontal asymptote and it involves leading coefficients. Or I can answer it with the calculus side of things. If I'm looking for x to go to infinity for x cubed over x cubed plus 1, that's currently infinity over infinity, but if I divided everybody top and bottom by x cubed, then I'd be looking at x cubed over x cubed, which is 1, x cubed over x cubed, which is 1, and 1 over x cubed, which is just 1 over x cubed. And as x goes to infinity, the top is going to 1 and the bottom is going to 1 plus 0. So in other words, we're going to have, as we go to the far right, the y values are getting close to 1. And similarly, on the left side of things, if you're looking at x going to negative infinity, it's also going to go to positive 1 for exactly the same reason. After we rewrite this, it's x going to negative infinity of 1 over 1 plus 1 over x cubed, which again goes to 1 over 1 plus 0, or 1. So in other words, horizontal asymptote y equals 0 on both sides. So I'll plot some of that in actually right now before I forget to do that. So I'll put in my vertical asymptote, x equals -1, and I'll put my horizontal asymptote, y equals 0. And I've got my one point on the curve that I know, which is just the origin, 0, 0. Okay, so I've got the beginnings going here, so now let's move our way upwards and figure out what's going on as far as increasing and decreasing and curvature. So we've got our function, so first thing we'll want to do is find our first derivative. And for that, of course, you're going to need quotient rule and all the rest. I have already done the work on this one, so just in the interest of time, I'm going to put down what I found at the very end for my first derivative, and I found that to be 3x squared over x cubed plus 1 whole thing squared. So for this one, if we're thinking about critical numbers, I know that f prime is undefined at x equals -1 for sure, because there's a vertical asymptote there. And if we're thinking about where f prime is equal to 0, Well, it's at the same place where we had our x-intercept. It's where the numerator is equal to 0, or 3x squared is 0, which happens to be 0. So we know that for critical numbers, then I've got 2 to concern myself with. I have a -1 and I have a 0. The -1, of course, that's a vertical asymptote, so it won't be any sort of max or a min, but we still do need to account for it. And if I look at my derivative, in fact, if I'm feeling really clever, I don't really need to evaluate anything. Um, because if you'll notice, the denominator is a perfect square, and the numerator is 3 times a perfect square. No matter what I put in for x, the numerator will be positive and the denominator will be positive. If you don't believe that, of course, you can always confirm that with your calculator and find out that f prime of, let's say, -2 definitely is positive, so we will be increasing on the left side of -1. And then between -1 and 0, let's go for a -0.5. And you'll find for that it's also a positive first derivative. You're increasing there as well. And at 0, after that, if I were to pick a value of, let's say, +1, and put that in my first derivative, I'd have 3 over 2 squared. That's a positive number. Again, you're increasing. So the one thing that we know is at no point do we change from increasing to decreasing or decreasing to increasing. So big conclusion, there is no max and there is no min. So there's no relative extrema, I could just say in general. So our function is going to always be going up, which means that that 0, 0 that we found as a critical number, not a max, not a min. Maybe it's a point of inflection. I don't know. We'll have to wait and see what we find out when we look at the second derivative. So first derivative, we already had it. And then second derivative, if I were to find that, it cleans up to give me 6x minus 12x to the 4 over x cubed plus 1 cubed. And for this one, again, you can already see that it's undefined at the same place as before. And if we're looking for where the second derivative is equal to 0, that would be where the numerator is equal to 0. And if we're looking for that, where 6x minus 12x to the 4 is equal to 0. That would be where 6x times 1 minus 2x cubed is 0. And that gives us 2 places to concern ourselves with. One of them is at x equals 0, the same old point we've had before, 0, 0. So for that, we've got x is 0 and y is 0. The other place that we have is when x is equal to cube root of a half, or 1 over cube root of 2. If you went back and found out what the y value is by putting that into the original function, so y value is f of 1 over cube root of 2. So if we put that back into the original function, you'd have half over half plus 1, or half over 3 halves, which is 1/3. So y value for that point is 1/3. And now let's do our little number line business. So we've got 3 points to put on our number line. We have the -1, and we have the 0, and we have the 1 over cube root of 2. 1 over cube root of 2, by the way, that is around 0.8, somewhere around there. So when I'm looking at picking my numbers, I'll pick something less than -1. So I'll pick, let's say, -2, and put it into my second derivative. I'll pick something between -1 and 0, so I'll pick -0.5. Between 0 and 1 over cube root of 2, so 0 and 0.8, I'll pick +0.5. And then for bigger than 1 over cube root of 2, I can pick 1. And so the one thing that we're going to find is that after I evaluate my second derivative at all of those points, I find that at -2, the second derivative is positive, which means we are concave up. At -1/2, my second derivative was negative, which meant we're concave down. At 1/2, it was positive for my second derivative, so we're concave up. And then at +1, the second derivative was negative, which meant we were concave down. As far as the points of inflection go, a reminder again, the -1 was a location of a vertical asymptote. So although we look like we're changing concavity, -1 is not a point of inflection because, too bad for us, it's not a point. However, 0, 0, that other place that we'd found that was a critical number, looks like 0, 0 is a point of inflection because we're changing concavity from concave down to concave up. And same thing with the 1 over cube root of 2. That's again up to point on our graph. We have an x and y point. There's definitely a tangent line there. It's a place you could put into your derivative. However, we're changing concavity, concave up to concave down. So we know that both of these places are points of inflection. So I'll make a little note to myself that I have points of inflection at 0, 0, and 1 over cube root of 2 and 1/3. And that's basically it. So we've gained one new point to put on our graph, which is 1 over cube root of 2, 1/3. So let's plot that. 1 over cube root of 2 is about 0.8 thereabouts, and 1/3 is about 1/3. So the point should be somewhere around here. And that's kind of that. So I just realized now as I was drawing things, I hastily put a horizontal asymptote at 0. You're probably wondering if I was ever going to correct this. So of course I'm correcting it now. I'm remembering the horizontal asymptote that we found was not y equals 0. The horizontal asymptote we found on the first line was y equals 1. I found a limit of 1 and then I foolishly put down y equals 0. So I've come back to correct things. Had I not corrected things, I would have noticed a problem later on with things contradicting each other. So I would have run into a problem with, in particular, my graph needing to continue to increase, yet somehow make its way back down to a horizontal asymptote at 0. That wouldn't have made sense, and that would have been, in fact, that's how I noticed that things were wrong here on my function, because I was thinking about how this graph increases all the time. So now I'll plot the real horizontal asymptote y equals 0, y equals 1 down. Okay, and now we can put everything in that we need. So the first thing that I'll make a note to myself of is we're increasing all the time. And so if we're thinking about on the left side of our horizontal asymptote, we are increasing, we're always heading upwards, so we're heading upwards to positive infinity as we get close to that vertical asymptote. The other thing that we know is that in this region, to the left of that horizontal asymptote, we're concave up, which makes sense for us to be concave up, because if we're heading up to infinity and we're also concave up, that would allow me to get to that horizontal line y equals 1. On the right side of my vertical asymptote, again, we're increasing all the time. I begin by being concave down until I get to 0, 0. And then we have that change of concavity where we're concave up for just a brief second. And then at our second point of inflection, we change concavity again back to concave down. So I'm just going to make that look a little bit nicer. So we're moving from concave up, concave down to concave up, back to concave down, so that we're still increasing and getting closer and closer to our horizontal line y equals 1. And I guess last thing for me to do is just label my point, 1 over cube root of 2 and 1/3, and then I can just label my function somewhere over here. So this is f of x is x cubed over x cubed plus 1. Nice. So if we go back, we can see that we hit all the facts that we found, that it's increasing all the time, increasing followed by more increasing, concave up followed by down, then up, then down. We have our vertical asymptotes and horizontal asymptotes happening. So I feel pretty good about this curve sketch. Let's do one more rational function. So this one, if I were doing a quick little factor of this, or factorization, we can see that the top factors fairly nicely. And that's going to allow me to see and say a couple of things. So namely, first off, I know that I've got two x-intercepts, because those are the places where the numerator is 0. So I have x-intercepts at -4, 0, and at 2, 0. For y-intercepts, that's where the x value is 0. And if we find where the x value is 0, or let x be 0, then we'll find that the y value is +2. So -8 over -4, which is +2. And the other part that we know, courtesy of the denominator, is that we have a vertical asymptote x equals 4. So actually lots of pre-calc information already. 2 x-intercepts, 1 y-intercept. We've got a vertical asymptote. Also, if we're thinking about horizontal, I mean, definitely not a horizontal asymptote because the top has the bigger degree, but we do have a slant asymptote because the difference between the degrees is 1. So I know that I'm going to have a slant asymptote, and I can find that by doing a little quick division. So I'm just going to quickly divide, and I find, so x squared minus x squared is gone, 2x minus -4x is 6x minus 8, and then I multiply. And the thing that I care about, of course, is the quotient, because we remember that the function could now be written as x plus 6 plus our remainder over our divisor, and that the remainder over divisor will go away as x becomes very large, and that the quotient will be what we'll be left with. So in other words, we know that as x gets very large in both directions, that y will be approximately the same as the line x plus 6. So I'll have a horizontal, not a horizontal, I'll have a slant asymptote rather of y equals x plus 6. And I've got a bunch of points, so I guess I'm going to start plotting some of these things. So x-intercepts and y-intercepts and all the rest. I have -4 for my x-intercept and +2 for the other x-intercept. Y-intercept was 2, and I had a vertical asymptote, x equals 4. We'll do that one in blue. That's a little bit wobbly. And now I'll draw in my oblique asymptote while I'm at it. So that line, y equals x plus 6, would cross the y-axis at 6 and the x-axis at 6. So my line should be along those sorts of lines there. So I'll just label all those things, the x equals 4 and the y equals y equals x plus 6. Okay, so we've labeled all of our stuff. I guess now the last thing that I need to do is the calculus side of things. And I say last, but that's really just the start of a fairly large journey. So first things first, we find our first derivative. And if we find our first derivative, we'll find that it simplifies to give us x squared minus 8x over x minus 4, whole thing squared. So we know that for sure this derivative is undefined at x equals 4, and that's because we've got a vertical asymptote there, so that's no surprise. We know that the derivative is equal to 0 when the top is equal to 0, so two places. One is when x is equal to 0, and the other is when x is equal to 8. We should, of course, go back and figure out what our y values are for these 2 points. For the x equals 0, we already know where the y value is. The y value is our y-intercept, which is 2. So that we already know. So it looks like our y-intercept turns out to be some sort of critical number. That's kind of fun. And the other place that we had was when x is equal to 8. And if we go back to our original function, the y value would turn out to be 18. So if we're looking at this, we have 2 points that we'll be able to put on our graph. Well, we already have one of them, 0, 2, and the other one is 8, 18. And we may find out that we've got maxes or mins at those places. So let's figure out what's going on. So starting with putting on my critical numbers, I have a 0, and I've got a 4, and I've got an 8. So let's do that. And if we are looking at our critical numbers, I can pick something, let's see, something smaller than 0, which is -1. And if I put that into my first derivative, so if I put in -1, and calculate, I find that this turns out to be something that is greater than 0. The top turns out to be +7. The top turns out to be +9, and the bottom turns out to be +25. So we are greater than 0, and we are then increasing. So if I do the same thing for the rest of the intervals, between 0 and 4, I find that y prime when x is equal to 1 turned out to be something negative. So we are decreasing. So 0 was a point on our graph. We increase followed by decreasing, which means we are having a maximum at that point, at 0, 2, a relative max. Between 4 and 8, I could choose 5, and I found for 5 that my first derivative was also negative, so we're decreasing. And after 8, I could pick 9, and I found if I put 9 into my derivative, it gave me something positive, and so we're increasing afterwards. 8 was definitely another point on our graph. We decrease followed by increasing, so in other words, we definitely have a minimum at x equals 8 and y equals 18. So I've got some things to think about. I've got 0, 2, and I've got 8, 18. I should probably plot that on the graph before I forget. So 8, 18 should be somewhere around there. And I know that one's a minimum, and I know 0, 2, that one is a maximum. And I kind of already have enough information to fill in what's the rest of the graph, but I want to just be confident that I'm not missing any points of inflection or anything else that might be going on. Of course, because there could be points of inflection on this graph. Maybe there are, maybe there aren't. So let's take a look at now our second derivative. So we had our first derivative, x squared minus 8x over x minus 2 to the 4. And then when we find our second derivative, this one turns out to be, after we simplify, just 32 over x minus 4 cubed. So for sure it's undefined at 4. That much is, again, not a surprise. The derivative, second derivative rather, undefined at 4 because the first derivative was undefined at 4, and that's because the function was undefined at 4. So there's no news there. The second derivative, though, is never equal to 0. And that's because if the second derivative were equal to 0, then the top would have to be equal to 0. But the top is always 32, so that means we're never going to have a second derivative that's 0. So the only place where we have where concavity could change is at 4, which is our vertical asymptote. And if I check to see what's happening with my second derivative on either side, so for real ease of use here, if you put in 0 for x, you'll find that the second derivative is negative, which means you're concave down. Not a surprise, because in this interval we've got a maximum, so I was expecting it to be concave down. And if I went for something bigger than 4, let's say at my other critical number of 8, I mean, I already know that that second derivative should be positive, concave up, and in fact it is. If we put in 8 for x, we get a positive number in our second derivative. So no actual points of inflection. 4 is not a point of inflection because 4 is the location of an asymptote. So even though we're changing concavity, it's not a point of inflection. So I was right when I thought about if I have enough information to graph everything. So for example, 818, that's a minimum, and I know we are going to be, after that point, increasing, and I'm going to be increasing and getting close to my oblique asymptote. So after I leave that point, I'll start trending upwards. And as I head to the left, I'm heading towards my vertical asymptote, and I know I was decreasing between the vertical asymptote and 818, so I guess I must be heading up to positive infinity there. At 0, 2, I know that that's my max, and from there I'm going to head to my 2x intercepts. And I know that I'm decreasing on the left side of my maximum, so I'm heading on downwards and getting close to that oblique asymptote. And on the right of the max, I'm also going to start heading downwards and heading to that vertical asymptote. And so there we go. This looks like this should be the graph of y equals x squared plus 2x minus 8 over x minus 4.